Hey everyone, so if you're a developer, you've probably typed mymap.put, I don't know, thousands of times. It feels so simple, right? It's instant, it's almost like magic. Well, today we're going to pull back the curtain and look at the surprisingly complex and honestly brilliant journey that single line of code kicks off every single time.
Right? It's this tool we all just reach for. It's part of our muscle memory. But that one simple command unleashes this fascinating, highly optimized chain of events. So let's actually answer that question. Let's find out what's really going on under the hood.
Okay, so at its core, a hash map is all about one thing: speed. Think of it like a super sophisticated filing cabinet for your data. It's designed so you can find exactly what you're looking for almost instantly without having to rummage through every single file to find it. And this right here illustrates the magic perfectly. With a regular old list, if you want to find something, you might have to check every single item. That's what we call O of n complexity. It gets slower the bigger it gets. But a hash map? It's built to jump directly to the right spot. It's the difference between walking down a whole street looking for a house versus just having the exact address. That's O of 1, or constant time, and it's what makes hash maps so incredibly powerful. So how does it do that? How does it find that exact address for your data without searching? Well, that brings us to our first deep dive, finding the right spot.
It really boils down to this simple two-step process. First, it takes the key you give it and runs it through a special function to create a number called a hash code. Then, it uses that number to figure out exactly which slot or bucket in its internal array your data belongs in. Let's break that down.
Okay, so first up is getting a good hash code. Now, this formula might look a little intimidating, but the idea behind it is actually pretty clever. Its whole job is to take your key's original hash code and just mix it up. It spreads the bits out. Think of it like shaking a can of spray paint to get a nice, even spray. This bit mixing is the first line of defense against different keys all trying to cram into the same spot.
So once we have that nicely mixed up hash, we need to find its actual spot in the array. Now, you could just use the modulus operator, the percent sign, but that's actually kind of slow for a computer. So instead, the hash map uses this much, much faster bitwise operation. That ampersand there, it's basically a performance hack that does the same job, giving us the final bucket location in a fraction of the time. It's these tiny optimizations that add up.
But even with all that clever math and bit mixing, the system isn't perfect. Sometimes two totally different keys will just happen to land on the same exact index. This is what we call a collision. So what happens then? Let's find out how the hash map handles a crowded house.
Well, the hash map actually has two strategies up its sleeve. The default move is simple. When a collision happens, it just chains the new entry onto the old one, creating a little linked list in that one bucket. But, and this is the brilliant part, if that list starts to get too long and slow, the hash map automatically upgrades it, transforming that clumsy list into a super efficient structure called a red-black tree. This keeps searches fast, even in a crowded spot.
So when does this amazing transformation happen? It all comes down to this magic number, 8. The moment a single bucket has 8 different entries all colliding in it, the hash map says, all right, that's enough, and it flags that bucket for an upgrade. This number, it's actually called the treeify threshold, and it's a carefully chosen trade-off point where the performance gain from a tree is worth the effort of building it. But hold on, there's a catch. This whole upgrade to a tree thing, they call it treeification. It only kicks in if the hash map itself is big enough, meaning its total capacity is at least 64. Why? Well, if the map is still really small, it figures it's just cheaper and easier to resize the whole thing instead of creating these complex little trees in tiny buckets. It's another one of those smart, built-in optimizations. And speaking of resizing, that's a really fundamental part of how a hash map stays healthy and fast. Which, of course, brings us to our next section, growing pains. So, how does a hash map know when it's time to get a bigger house? It has this internal sensor, and it's called the load factor. The best way to think about it is like a fill line on a measuring cup. Once the stuff inside hits that line, it's time to pour it all into a bigger cup. And by default, that line is set right here at 0.75. What this means is that as soon as the hash map becomes 75% full, bam, it triggers a resize. This is all about being proactive, making sure there are always enough empty buckets to keep collisions rare and those lookups lightning fast. Now, the resize process itself is, Well, it's a bit of work. First, the hash map creates a brand new, bigger array, usually double the size of the old one. Then, and this is the really intensive part, it has to go through every single entry that's already in the map and recalculate its new home in that bigger array. This whole rehash operation is absolutely vital for keeping performance great as the map grows.
All right, so we've journeyed through hashing, collisions, these cool self-transforming trees, resizing. It's a pretty wild ride. But the real question is, why does any of this matter for the actual code you write every day? So let's connect all these dots and talk about the real developer takeaway. So here's the bottom line. On an average day, which is most days, a hash map gives you that incredible O of 1 constant time performance. It's basically instant. And in the absolute worst case scenario, thanks to that clever upgrade to a tree, the performance only dips to O log n, which, trust me, is still remarkably fast. Now, to get all that power, you have to play by the rules. There are 3 golden rules. First, and this is non-negotiable, your keys have to have properly implemented hash code and equals methods. If they don't, the whole system just falls apart. Second, never, ever assume the items will be in any particular order. They won't be. And finally, if you've got multiple threads trying to access your map, you need to use a concurrent hash map instead. It's built for that. A regular hash map is not. And that really brings us to the core idea of this whole explainer. It's one thing to know what happens when you call put ed, but it's a completely different level to understand why it happens. Why mix the hash? Why turn a list into a tree? Why resize at 75%? That deeper understanding of the why, that is what separates a good developer from a truly great one. So I'll leave you with this question. The hash map is just one of the amazing tools in our toolkit. What other fundamental structures are you using every day without really knowing about their own secret journeys? It's worth finding out. Thanks for digging in with me.